Welcome back to the classroom. My name is Mr. Wong, and today we'll be looking at Module 5, Advanced Mechanics, Inquiry Question 2, Circular Motion, and we're going to be looking at this particular dot point for today. Our lesson title, Stop the Torque. Our lesson intention is to investigate the relationships between or affecting the rotation mechanical system, so how things rotate, and we're going to analyze the relationships between variables to maximize our rotation, or what we call torque. So torque is about the turning moment of an object. There are only a couple of variables involved, so let's go through it. We can also apply this on DC motors and also, well, not DC motors, AC and DC motors and generators, using the same concept that we talk about here. Okay, so what is torque? Torque is a rotational effect that a force has on an object, and we refer that as torque. It is not a force, it is an expression to show how the force is affecting an object's rotation. Okay, it's represented by the letter tau, Greek letter here. It is a vector, so you need to also state the direction in which it's spinning. Okay, in a separate video, I'll look into some factors that influence torque. And that is using this little simulation here. I'll also do a little demo as well following on. So look out for that one as well. So some factors that influence the magnitude of torque. Point one, it's the distance from the pivot point. What we mean by the pivot point is the point at which the object gets rotated by. So if we're looking at a wheel on a bike, that's our pivot point there. If we rotate the bike at this distance here, we will be able to generate a greater rotation. Notice how I say a rotation, not force. We'll generate a greater rotation than this one here if we began the rotation at a smaller length away from our pivot point. So length from pivot point, one crucial factor. Our second point is obviously the force, but we're also looking at the angle in which we apply to the force. Now, in this diagram we have here, when we apply perpendicular to the length, so maximum force is achieved if the length of that point and the force you apply is directly perpendicular to each other. That's where you get maximum force. If by any chance we apply it at an angle to the pivot point, so the force that we apply is at an angle to which the pivot point is, then we need to solve for the perpendicular component of the length in order to find the force. Okay, so that's what we have here. To put it simply, we can demonstrate it with this formula. So this is the formula for torque. Okay, tau equals to the perpendicular force to the length of the pivot point. Now force, to get maximum torque, the force has to be perpendicular to this length here. You can see with our diagram, this length that we have here is not perpendicular to this length we have here. So what we need to find is the perpendicular component of that side. You might need to draw it. You might be able to picture it out. This is what we have here. So using our formulas, we know that this is sine theta here. This is sine theta here. We're approaching the angle to the pivot point. So we can solve this using trigonometry. This is our hypotenuse. This is our opposite side, so we can use sine theta to help us solve it. And so you can get a general equation that looks a bit like this. another way of factoring is if the handle looked like this. So we're saying maximum is if we touch it perpendicular like this. Now, what if I try to push at 0 degrees or 180 degrees? So I'm directly parallel now to the length. What if I pushed it? What if I pulled it? Well, I might be able to move it if it's not attached to anything, but I would not see a rotation. So at 0 degrees, I get no rotation. At 90 degrees, I get maximum rotation. So the best sort of trig ratio that can help demonstrate that is sine theta. Because when sine theta is 0 degrees, it is 0. If sine theta is 90 degrees, it is 1, which is the maximum number you can reach. So that's why we use sine theta here. Okay, so some factors that influence the magnitude, we already talked about it, the distance from the pivot point. Okay, so the distance between the pivot point center and the line of action of the force, that's what we have here, and the angle of the force applied to the perpendicular radius. Those are two really important factors that will influence how much rotation you see in your object. Okay, so put it simply, torque is the amount of force used to rotate an object in a particular direction. You use this formula if the force that you apply is perpendicular to the distance or the length of your pivot point to length of pivot point. If not, then you use this formula here. Torque is Newton meters. As you can see, that's newtons. That's measured in meters. So Newton meters, not Newton per meter. That's a different measurement. So there's that. Radius measured in meters and force obviously in newtons. Let's do some calculations. So we have a bus driver applying a force of 45 newtons, and they do a right hand or turn at a right hand corner. So they're rotating clockwise. The radius of the steering wheel is 30 centimeters. If the force applied was 90 degrees to the radius, what is the torque? So we simply use this formula here. Because it's perpendicular, 90 degrees, we get a maximum torque. We have 45 newtons times 30 centimeters. Now that 30 centimeters needs to be converted into meters. Okay. And what we get would be 13.5 Newton meters clockwise. You could probably draw out the direction, that might help as well. And our next one, a student uses a 42 centimeter long adjustable spanner. Okay, so 0.42 meters. To loosen a nut on her bike, she applies a force of 65 newtons at an angle of 68 to the spanner. So if the spanner was, let's say, here, okay, and this is our length now, we drew out. So this is for the 90 degrees. This is the object, and this is the 68 degrees. 68 degrees. Okay, what is the magnitude for our anti-clockwise torque? Well, it'd be torque equals to F radius sine theta. It would be 65 times 0.42 times sine 68, which gives us a torque of about 25.3 Newton meters. We don't have to write anti-clockwise because it's already written for us. All right, question 3, we'll go through another calculation. We have a 1.2 meter wide gate in a school fence. Oh, it will only open if the torque is 100 Newton meters plus. Which of the following cases will the force applied be resulting in an open gate. So using the first one, we have torque, we have a force, and we have a specific distance. Now, in this example, there is no angle, so we can just substitute it as we do. We get 60 Newton meters, and we are going anti-clockwise because we're pushing up, so the door will go backwards. Well, all of them will be anti-clockwise, but there is no opening. As you can see, because this number is smaller than that. B, same idea, but this time we're further back. So 100 times 1.2, so we get 120 Newton meters. Again, anti-clockwise. And this time it will open because the value of torque we have here is bigger than the torque that's stated here. C, what if we did it at an angle? So it's 30 degrees, which means that the torque we want to find is this perpendicular component of the triangle. So let's have a look. We have torque. It's 120. It is a radius of 1. And it's sine 30 degrees. And that gives us approximately 60 Newton meters, again anti-clockwise. And again, as you can see, it will not open because it's just too low. Okay, so that's how you do that question there. All right, let's go through some multiple choice questions. According to the System International SI units, what is the unit for torque? Where should a force be applied to a lever to maximize the torque? I'll give you 5 seconds to pause this and then we'll go through the answers. Okay, so answer for A is A, Newton meters. Answer for question B is B, the furthest from the pivot point. Okay, so we've reached the end of our lesson for today. This is a question from the 2019 HSC physics paper, which it asks you to justify the validity of the student's model using the information of our graph here, and what happens to the model's accuracy as we increase beyond 25 degrees. I'll let you have a think about that. There is an explanation video on it. Links will be in this video as well, but that's what you need to do. Anyhow, thank you for joining for today's lesson about torque. Here's a little summary of all the different notes we talked about. If you found this video useful, give it a like, subscribe if you haven't done so already, and I will see you next time. Thank you for paying attention.